Recording in progress.
Can you guys hear me now?
Yes.
Okay. Somehow it got disconnected in between. Okay. Anyway, so we are writing X as ABC. And finally, the conclusion is that no matter how many times I repeat the middle piece, I'm going to stay within the language. Okay. So just the fact that there is one string of length more than p in the language, you get many other strings that are in the language. Okay. So we saw one example use of this in the last class, and today we will see a few more examples and then kind of try to understand why such a statement should be true for finite automata. Okay. Any questions about the statement? Okay. And the way we will use it often is in its contrapositive, meaning, so this is saying that if a language is regular, then something is true. Okay. So we'll use it in proof by contradiction. So if we show that for every number p, there exists some string x such that you cannot split it up to satisfy the conditions of the lemma, then the language must not be regular. Okay. Yeah.
Does I have to be greater than 0?
Greater than or equal to 0. It can be 0 as well. In fact, in some proofs, it is useful to take I equals 0. It might simplify it. You want some chocolate? All right. Okay. So, all right. Okay, so let's do one example and then kind of, we'll see where it leads us. Another example, I should say. So let's say example number 2 is, it's kind of a simple language, but we'll see why it's useful. So I want to look at all strings which are of the form 0 to the k, 1, 0 to the k, where k is some number greater than or equal to 1. Okay, meaning I have some number of zeros followed by a 1 and then some same number of zeros. Okay, like 10 zeros, 1, 10 zeros. Okay, so this is my language. All right, so I want to claim that L is not regular. And the way we'll think about it is, let's suppose if the language was regular, then something should happen. What should happen? There must exist some number p such that pumping lemma holds, right? The conclusions of PL holds. Okay, so let's pick 6 number p. It's maybe 1,017,000. It doesn't matter. Okay. Now the name of the game really is in us coming up with a clever choice of the string x, right? So the lemma says that any string more than, or at least as long as p bits long, must have a piece which can be repeated. Okay. So let's pick one such string to try and get a contradiction. Somehow there are some strings where repeating them would cause you to be outside the language. Okay. Any suggestions on what such a string might be? So we know that for every x, which is of length more than p and in the language, you should be able to split it up. So let's pick one such string and see what happens. Okay. So what is one such string, which is clearly of length more than p and in the language? Let us try what happens if x equals 0 to the p, 1, 0 to the p. Meaning I just have 0 repeated p times. There is a 1 and then 0 repeated p times. Okay. So this is my candidate sort of rebuttal to the statement that the language is regular. Okay, so I'm saying, okay, here's my string X. Can you tell me how to split it up so that you satisfy the conclusions of the lemma? Okay, what's your way to split it up so that one of the pieces can be pumped or repeated? Well, let's see, right? No matter how I write X as ABC, I split up X as ABC to satisfy the conditions of the lemma, what should happen? Can anyone tell me why you might end up with a contradiction? So this is my X. I need to split it up as A, B, and C, right? And I have these three properties, remember? These three. So the third property is often kind of, makes the argument simpler. So let's look at the third property. So what does the third property say? It says that the length of the first two pieces is no more than P, okay? But my string X starts with P zeros, right? So by PL, we must be able to split X equals ABC, okay? Now, the length of A and B put together is at most P, right? So together, if you kind of start aligning them, then this A and B should end before you see P bits, okay? But they should always match, right? Because you're just splitting up X exactly. So what can B be? Must be only zeros, right? Because X is only zeros at the beginning, right? So this implies that B is made up of only zeros. Okay. And now I want to say that you're done. Why? You should be able to get a contradiction because, any suggestions? Yeah. Exactly, right? So if I pump the B one more time, then A, B, B, C will have more zeros before the first one. Okay, which is a contradiction. Because when you have more zeros than the first one, is not in the language, but pumping lemma says it should be. Okay, so this is a contradiction. Okay, so the only assumption that we made was that L was regular. So implies L is not recognizable by a DFA. You want some candy? Which one? Yeah. Okay. All right. So let me just kind of give a caricature of this argument. Yeah. Yeah, that's a very good question. So let me the question. What if L has finite size? Maybe L had just like 10 strings within it. What would the pumping lemma say about it? And somehow it's saying that just the fact that a single string is in the language should imply that a lot of other strings are in the language, but my language itself has only 10 strings. So how is this not a contradiction? Any suggestions? And what's the resolution for it? Yeah. Exactly, right? So we get to choose P after you see the language. Okay, for every language, there is a P. Okay, you should think of P as roughly saying something like, okay, it's like any automata that needs so many states must have some property. Okay, so assuming you also wanted tricks. Yeah or no? Okay, you? Sure. Okay, so the answer is that P could be higher than the longest one in the finite set. Okay, so then the lemma would be true kind of in the trivial way, right? It's becoming vacuously true. There is no string X which is of length more than P, hence, it's true. But basically it only says something about strings which are sufficiently long enough, right? Okay, so that kind of is a good lead to how to think of applying the pumping lemma, right? So imagine there is Alice, okay, and there is, maybe I'll inspired by my costume, I'll draw him with one eye, Bob. Okay, so there is some language L here, which is whatever, maybe L is X such that X equals 0 to the K, 1, 0 to the K, K is greater than or equal to 1. Okay, there's some language in the sky, right? They're having a debate whether or not this function or this language is regular. Okay, Bob comes and says, hey, this language is regular. All right, so Bob claims L is regular. Okay, Alice doesn't trust Bob. So she says, okay, so if it is regular, tell me what your P is. Tell me what your P is for which pumping lemma holds. Okay, then now Bob is kind of, has to respond. He says, maybe try P is a million, whatever. Okay, some number. So often we work with the setting without any specific value for it because Bob can respond with whatever Bob wants. And Alice would like to refute or verify this, right? And then Alice says, if this is your P, tell me how to apply the lemma. How do you split up this particular string X? Here's my challenge string X. Tell me how you will split it up. Okay, and if Alice is clever, she'll pick a string, something like this, and Bob gets caught, right? There's no viable strategy for Bob at this point. Like for instance, Alice sent across 0 to the P, 1, 0 to the P, and then Bob is lost. Okay, maybe I shouldn't even call it Alice. I should call him Kakashi. Okay. All right. So any questions about this template? So always imagine that if someone's asking you to check whether language is not regular, you're kind of playing the role of a pessimist and you're trying to guess what's the best challenge string X to question this premise that the language is regular. Okay, let's do a couple more examples and then we'll see why the lemma is true in the first place. All right. Okay, so example. And this is the language palindrome. Okay, so palindrome is all strings X such that the string and its reverse are exactly the same. Okay, so and recall that reverse of X is list of bits in X written in opposite order. Okay, so we're just going from right to left instead of left to right. All right, so for example, some string like 1001, 01010, these would all be within the language, right? Because they read the same from left to right as from right to left. Okay. And if someone came to you and asked you to design, okay, tell me how you can compute, is it possible to compute palindromes using a finite automaton? Then what would you do and how would we fix it? How would we check whether or not that is possible? Okay. So let me cheat a little bit and tell you the answer, but let's try and investigate why that is true. So the claim I want to make is that palindrome is not regular. Okay. And if this is what we're trying to show, then what would we do? We'd imagine playing our game, right? So there is, you suppose that palindrome is regular. Okay, so Bob claims that palindrome is regular. Then Alice asks, okay, is, what is your P? So you'd say there is some finite number P such that the pumping lemma conclusion holds. And now we get to pick, we have to choose a string X wisely so that it's hard for Bob to split it up. Okay. So, let's try something first, right? And see what happens. What if I choose my string X to be something like, maybe 01 to the P and followed by a 0. Okay, so this is something like 010, 01010. These all read the same, right? Okay, so this is part of the language. Okay, so first attempt. Okay, this is a nice enough string which is in the language, and Alice says, okay, here's my challenge string to Bob. What does Bob do then? Can Bob split up the string as ABC where one piece can be pumped? Yes or no? So what would we want to do, right? So Bob would like to split up this X. There's some sequence of 0s repeated P times, followed by a 0. Yeah? A can be empty. The only thing that's not allowed to be empty is B. Exactly, right? So B can just be 01. So Bob says, okay, here's my split. So this is B, C is whatever is left, and A is the empty string. Okay, so maybe let me write it in words. So take A equals empty, string, B equals 0, 1, C equals whatever is left. Okay, so under this split, I can write X as A, B, C, and I don't get any contradiction because no matter how many times I repeat B, I'm still within the language. Okay. Why? So let's check that. X equals ABC. What is A times B times B times C? It's just 0, 1 repeated 2 times, followed by P minus 1 times, followed by a 0, right? So this is just P plus 1 and 0. Okay, so what's happening here is we picked a string X, which can actually be pumped. But does this imply that the language itself is regular? No, right? It only works one way. It's not an if and only if statement. The pumping lemma is not an if and only if statement. It doesn't say that something can be pumped. If a specific string can be pumped, it doesn't mean anything. You have to check it for all strings, right? So Alice's challenge fails because X can be split up so as to satisfy. Okay, so let's try again. What's a better string? What's a better challenge for Alice to give to Bob? Yeah. Okay, so let's try X is 0 to the P and a 1 and a 0 to the P. Okay. Now this is also in the language, right? You want some candy? Which one? Okay, so the second suggestion is let's try X, which is 0 to the P, 1, 0 to the P. Now I think we caught Bob in his lie. Let's see why. Okay, so this is X, and now suppose I split it up as A, B, and C. What should happen? Again, it's the same argument, more or less, right? So the length of A and B put together is at most B. So B can only be zeros, right? So length of A and B together is less than or equal to P, implies B is only zeros. Okay. But then A, B, B, C is not a palindrome. Right? Because if I repeat B 2 times now, I will have more zeros before the 1 than afterward. So if I read it from left to right or right to left, I will see a difference. So it's not in the language, right? So because there will be more zeros before the 1 than after it. Okay. implies a contradiction. Okay, so therefore, we can say that palindrome is not regular. Okay, any questions about this overall template of argument? Okay, so let's do one last example and then we will see what happens. Okay, so the last example is, last example that we are going to look at. So actually, I should say that we are looking at somewhat intuitive examples where it is easy to guess what the challenge string is. Okay, but some cases it might actually be pretty hard to come up with the challenge string. It's kind of where the ingenuity in trying to decide whether the language is regular or not comes in. Okay, and the homework will identify one such case with some hints. So hopefully you'll see some intricacies there. Okay, but let's look at one more simple example. And this corresponds to, maybe a little bit like, so let's say, okay, so all strings with only ones and number of ones is a square. Okay, someone told you, okay, it's a little bit like computing the square of a number using finite automaton, I think, roughly speaking, but it's formulated in a different way here. I'm saying, okay, can you tell me whether the number of ones in the sequence is the square of a number? Is it 4? Is it 9, 16? I give you some huge number of ones and I tell you, okay, tell me, is this a square of an integer or not? Okay. And claim is this is not a regular language, but they should say L. So we suppose that L is regular. And if it is regular, then there is some number P such that pumping lemma holds. Okay, now comes Alice's turn. What challenge string should she choose for this language? Okay, in some sense, there are even fewer options, so maybe the task is a bit easier because it's only made up of ones. But tell me, what challenge string should Alice choose? There are only a few tweaks left. So what should Alice choose? Give me one suggestion. Yeah. Okay, let's try 1 to the p squared. Right, so 1 repeated p squared times. Okay, here you go. Okay, so it is definitely of length more than p, so we can apply the lemma. If I ask you to split it up, so by the pumping lemma, we should be able to split up X as A, B, and C. Okay. And the main things that we know are that the length of A and B put together is at most P. And because X is made up of only ones, all the pieces should also be made up of only ones. Okay. And now I want to claim that if I look at B repeated 2 times, then this is not in the, okay, let me ask you, is ABBC in the language? Any guesses? Could that be in the language or is it not in the language? Okay, if not, why? Yeah,
So the next square is p plus 1 square, which is p square plus 2p plus 1.
exactly. Right. So tricks again. Okay. So if I repeat B, then B is of length at most P, right? So when I add this extra piece, the length of this new string is actually at most whatever your old length was plus P, right? Recall length of AB together is at most P, implies length of B is at most P. Okay. Can this be the square of a number? P squared plus P? No, right? Because we have P squared. If I try and write down the squares of numbers, the next square is P plus 1 whole squared, which is P squared plus 2P plus 1. So this number will be somewhere in between. So it's not equal to the square. Okay. Strictly less than P plus 1 whole squared, the next square. So implies A, B, B, C is not in the language. Okay, so we actually have to be a little bit careful here, right? Because if you repeat B 2 times, then you might end up being in the language actually. Okay, or maybe if you repeat it 3 times, then you might end up being in the language. But we know that at least one repetition doesn't give you back in the language. So this implies that we have a contradiction. Hence, the language is not written. Okay. So, this is how you can at least reason reasonably well about why some languages are not computable by finite automaton, right? I mean, if everything was computable by finite automaton, things would be very simpler, right? Very simple, because as we said, when you think of them as algorithms, they are the simplest possible algorithms. They make a single pass over the data, they have finite memory, so very easy to implement and very fast, even in practice. Okay, so let me say some remarks. So pumping lemma gives us a, I would say, somewhat mechanical, but there's still some cleverness sometimes required in how you choose the challenge string. But there is a recipe, gives us a recipe to confirm that some languages, some functions, let's say, are not computable by DFAs. Okay, and often showing something is not computable in some model is very useful because it can serve us as guides in trying to design better models, as we will see, and also kind of stop doing futile searches, right? Okay, and should some kind of this is something that we're not going to cover in this course, but just as a remark, there are languages that are not computable. By DFAs, but you cannot prove this by pumping them. Okay, it's a very nice kind of clean recipe for trying to show that many languages or many functions are not computable by finite automaton, but it's not a complete method. Okay, so there are some functions which are not computable by finite automaton, but require some other techniques to defeat them. Okay, yeah.
Is there proof for the pumping lemma?
We are going to do it. We are going to do it. Yeah. And there is in fact a complete method to check whether or not a language is regular, but that's something we are not covering in this course. It is related to something called the Mihl-Nerode theorem. So if you're interested, I can tell you more about it in the office hours, or you can look it up online, but it's something that we're not going to touch upon in this course. Okay, yeah.
So does the second remark imply that there exist irregular languages that satisfy the pumping lemma?
Yes. Yeah, there are, reasonably simple examples of irregular languages which would that satisfy the pumping lemma. So it kind of, says we have some other methods, and fortunately, even like a complete characterization of what regular languages can be. Okay, and this comes from this very famous theorem called Mihl-Nerode theorem, but that's something that we're not going to cover in this course. Okay, so let's take a 5-minute break, and when we come back, we'll see why the pumping lemma holds, and kind of the proof will be by picture, as you'll see. Okay, all right, let's take a break. All right, let's get started. Okay, so as I said, the proof will be kind of by a picture. So let's start with what we're trying to show, right? So we're trying to check. Someone is telling you the language is regular, meaning there is a DFA that computes the language L. Okay, so let's call this DFA D. And if we are trying to prove the pumping lemma, someone gave you the language and told you that it is regular, we have to now find a number P for which the conclusions hold, right? And any suggestions for what we might choose the P to be? So we are trying to prove the lemma. So let me give a hint. So, okay, well, I'll answer it and then we'll see how to use it actually. So let P be the number of states in the DFAD. Okay, so what we're trying to show is that for every regular language, there is some number P for which the conclusions of the lemma hold, right? And we have the language that is regular, so that there is some DFA that computes it. Maybe it has 10 states, maybe it has 17 states, maybe it has 1 million states. It doesn't matter. There's some finite number of states. So let's pick P to be that number of states. And now we need to show that every X of length at least P can be split up as X equals A, B, C, such that the 3 properties hold. Okay, that's what we're trying to show. So let's start with kind of trying to picture what happens. So we have our X. I'm just going to write it in this way. let n equal be shorthand for the length of the string x. So it has n bits in it. I'm just numbering them 0, 1, 2 up to xn minus 1, right? And we have to show that it can be split up, right? It can be split it up. We can split it up into 3 pieces. And these are the individual bits of x, okay? And length of x equals n is greater than or equal to p. All right. What we're going to do is just track what the automata would do on this input, okay? So what would the automata do, right? So you start from some starting state, for us, which is typically 0, right? Which is 0. So let's call it S0. And then let's see if I can get the alignment right. Okay, so you read x0 and take a jump, okay, to some other state. Let me call it S1. After reading the first bit of x, remember we always index bits from 0, you jump to a different state. Okay, and then I read the next bit and I jump to another state. I read the next bit and jump to another state, and so on. Okay, and eventually when I read this last bit also, I jump to some state, and depending on what this last state is, we decide whether the string has to be accepted or not, right? Any questions about, we're just kind of walking through what the automaton would do, right? How many states do we have in this sequence? Just imagine I told you, okay, you're in state 1, state 10, state 17, state 19, and so on. For every bit you took, you see a jump. So just write down this entire sequence of states. How many states would we see here? Well, maybe I'm phrasing it in a more confusing way, but let me just say there are n+1 states here, right? Listed. Okay, I'm just listing out, you're in state 0, state 17, state 19, and so on. For every bit of x, you're taking a jump. So you're listed, written down n+1 states. And what do we know about n? The number of bits in the length, it's at least p. Okay, so this is more than p, the number of states in the automaton. Okay, so intuitively all we are saying is, suppose you have a finite automaton which has maybe 100 states within it. I give you an input of length 1000. What is something you can say for sure about the execution of the automaton? In the sequence, something should happen. Yeah, you have to repeat a state at least once, right? Because I'm writing down, n+1 numbers, where each number is something from a smaller range. There are only p possible values for it, because that's the total number of states in the automaton. But I'm writing down more numbers than the number of possibilities. So there has to be a repeat somewhere. Okay. Fix. Okay. So there's a fancy name for it. Do you know what's a fancy name for it? Yeah. Yes, pigeonhole principle. Okay. Here you go. oops, sorry. By the pigeonhole principle, we must have a repeat. Okay, so in this list of states that I visited, there must be a repeated number. Okay, just because there are only 100 possibilities and I'm writing down 101 numbers, so some two must be repeated. Okay. So if some two are repeated, I could, maybe just imagine redrawing this a little bit, right? That is Si equals Sj for some I not equal to j. Make sure I'm recording. Yeah. Okay. So let me just, so here I was just writing down the states in sequence, but now let me actually write it down as what happens on the automata, right? Maybe let's think of the path that you would take. Maybe you went from state 0, you took x0 and went to state number 4. Okay, and maybe you saw x1, you went to state number 17. Maybe you saw x2, you went to state number 1000. Okay, again, these are all arbitrary, right? You did this, did this, did this. You're in some state Si, but then you came back to this state. There could be other repeats, but all I'm caring about right now is that there is one repeat at least, and trying to find out, identify the first repeated state. Okay, so if I write down these numbers, there's 0, 1, maybe 10, maybe 11, but then suddenly I see a repeat. Okay, I'm just trying to identify what's the first number that is repeated. Okay, and pictorially it would look something like this, right? And then maybe you ended up in an accept state. So this is a rough picture of what happened. Right, I'm just writing down, okay, what my jumps were within the DFAI. I had some number of states. I saw a bit, I jumped somewhere. I saw a bit, I jumped somewhere, and so on. Okay, and I'm trying to identify the first repeat. That was the first repeated piece. Okay, and X is this whole string, right? I keep seeing, I'm reading one bit of X every time. Okay. So if I want to prove this lemma by a picture, I want to say that this already gives you an idea of what the split should be. Okay, this picture tells me, or I want to claim that this picture tells me what's a good way to split up X as A, B, C, where the middle piece B can be repeated. Any guesses? Yeah.
A is all the states up to the repeated, the first instance of the repeated state.
Okay.
B is the loop. B is basically the loop, and C is after the loop.
Okay, so let's see. Right, so this is, the suggestion is, let's take this to be A, and oops. Okay. Okay, and this to be B, and maybe this is C. Okay, so that's the suggestion. And the intuition is that you went around in a loop once, right? And you got somewhere. What would happen if you just went around the loop twice and then repeated the same thing that you did before? Where would you end up? The same spot, right? Imagine you went from a place A to place B, took a loop in between. No matter how many times I repeat the loop in between, I'm going to end up in the same destination if I don't change what happens afterward, right? So that's kind of the entire crux of the lemma, right? There is one state that got repeated. So no matter how many times I go on that cycle, it's not going to change where I end up in the very end. Okay, so the idea, take B to be the segment between the first two repeated states. Take A to be what comes before this loop. Take C to be what comes after. Okay. And just from construction, you can even, I mean, you can also see, right? If I went here, I went around B, and then I came down like this. Okay. What if I just did this? I would still end up in the same destination. So for instance, A and C would also be in the language. A and C would be in the language because I'm ending up at the same except state. A, B, B, C would also be in the language, right? Because if I repeat this loop twice and then take this C, I'm still following the same thing. Okay, and so on and so forth. So A, no matter how many times I repeat the loop, it's not going to change what will happen when I follow the instructions in C. Okay, any questions about this? All right, so we're mainly using the fact that there are only a finite number of states to argue that there should be a repeat, and we are just going to take B to be the repeated segment. Yeah. Sorry, say that again. Not necessary, because imagine, so what is this diagram saying, right? We took, kind of think of the bits in X as telling us, okay, follow this, jump, follow this jump, follow this jump. We take the jumps according to B, we end up here. And then we take the jumps according to C, we end up here. Okay. So all I'm saying now is you took the jumps according to A, you end up here. Now, let's say I don't follow any of the jumps executed by B, and I'm just going to repeat what C asked me to do. Then nothing has changed because B led me back to where I ended up. Not that it's an empty string. I'm just saying whatever B is, if I don't have B also, my behavior is the same. If I have B, it's the same. And if I repeat B 2 times, also it's the same. So these are like different statements. I'm not saying replace B with the empty string, but imagine that I just cut out this part of the instructions. Okay, like, I tell you, okay, the directions from going from here to somewhere, or take a left, take a left, take a left, take a left, take 4 lefts, and then take a right, and then a left, and so on. Right? The 4 lefts just brought you back to the same starting point, right? So I could cut that out and tell you what came afterward, and you'll end up in the same destination. Okay, yeah.
Can you explain again why is there a repeat?
Why is there a repeat? There is a, yeah, so there should be a repeat because the length of X is longer than the number of states that we have. So imagine there are only 10 states and my string X has 10 bits. I start from state 0, I see a bit, I need to go to a new state. It could be 1, maybe something new state, then it's like 5, 4, something like that. But at some point, I'm writing down a state every time I see a bit. But there are only 10 possibilities. So I need to see something that I've already visited because this length is more than 10 in this case, or more than P, which is the number of states in the finite automata.
What is the 10 possibilities?
That corresponds to the number of states in the DFA. Like imagine that I told you to write me a sequence of 11 numbers, each one only having 10 possibilities, say 0 through 9. And I'm saying some number should be repeated in the sequence just because there were only 10 possibilities. Okay, so and that repeat is what we are identifying. Okay, and kind of 10 and 11 are being represented by this P here, which is the number of states. Okay, does it make sense? Okay, more candy for you too. No? Okay, you. Okay. Any other? Yeah. Not guaranteed at all. There can be many loops. We're just identifying one loop. Like pick the first possible loop. You can pick longer loops, anything you want. Right now, we're just saying there's at least one loop and pick the first one for our convenience. Okay, if there are more loops, it's fine. Maybe this B itself is kind of, maybe there's another loop here. That's also okay. So there could be multiple ways to split it up, but all we are saying is at least one way to split it up. Yeah. Tweaks. Any other questions? Okay. All right. So let me formalize this. I mean, the picture kind of is more intuitive, I would say. When I write it down formally, it will be a little bit cumbersome, but hopefully it's okay. So let S0 is the starting state, which is 0 for us. And I'm going to define S1 as whatever the automata does on reading the bit. Okay, so transition function of the DFA. Okay. So S1 is, you saw whatever your automator asked you to jump to when you are in the starting state and you saw the first bit of X. S2 is whatever you jump to when you saw the second bit of X and so on. Okay. As the length N is more than or equal to P, there must be 2 indices, I comma j, where Si equals Sj. Okay. And I mean, these are 2 distinct indices where the state has been repeated. And the repeat has to occur even within the first P places. Okay. Any questions? I mean, I'm just writing down what was in the picture formally, right? So there must be a repeat within the first P things. So let's try and identify that. SI and SJ are the two things that got repeated. Okay. Now we set A to be everything leading up to SI, and B is the piece in between. And C is what comes afterward. Okay, let me say, could be empty. Could be empty. We don't care about it, but this is not empty. Okay, so that's the whole proof. You just identify the first loop. There's some loop, it doesn't matter which ones you pick. It's okay for us. Okay. Any questions about the proof of the lemma? All right. And I said by construction, no matter how many times I take the loop, I'll still end up in the same destination. Hence, I'll still accept the string. The length of A and B put together is at most P, because I need to see a repeat even within the first P places, because the number of states is only P. Okay, so there should be a loop even within the first P places. And maybe I change the order. Okay. All right, that's basically the proof of the lemma. There's nothing more to it besides the existence of this loop. All right. Okay. So with that, let me end the discussion on pumping lemma. And the main takeaway from that is, maybe it's not a big surprise, but at least it's good to know and have a rigorous way to reason about it, that DFAs are not enough as a model for computation. Okay, so recall our original goal, right? Our goal was to kind of come up with a good model for computation, which can capture what we think of modern computers is doing, right? We started with circuits because they are physically implementable, but then they had this problem that they could compute everything, but the problem was that they only worked on finite size inputs. To fix that, we introduced DFAs. But the DFAs, of course, the issue now, as it turned out, is that they're not very powerful. They cannot compute something simple like whether a number is a square, whether a string is a palindrome, whether a sequence of zeros and ones has more ones than zeros. These are simple functions that we think we should, we always write programs for them, right? So we should be able to compute them. But DFAs, are not able to do that, okay? So how can we fix this? What would be our next step towards that? Okay. And instead of going one step at a time and taking many, many small steps, our next step actually will take us to our final destination by itself, okay? And the model that we're going to look at next are Turing machines, right? And they're Turing machines. They're called that because they were introduced by Alan Turing in a really important paper in, I think 1936 or 32, forget. I think it is 1936. And this is a model that can deal with
Sort of unrelated question, but where do papers about computer science sort of begin? Obviously, it's a much more modern topic than say, mathematics. So what's like the dawn of the era?
Yeah, it's a very good question. I think, you can, I would say it goes back to many of these sort of equation solvers, like, Al-Kharzami, for instance, but also many people in 15th and 16th century where, like, Galois and so on, they were trying to find, they said, okay, I want to solve a quadratic or quintic equation. What they meant by that is they wanted an algorithm to do such thing, okay? And then people were doing all kinds of things, like even if you go 2,000, 3,000 years ago, like Euclid's algorithm for identifying the GCD of two numbers, it's an algorithm, right? So that's kind of, people had algorithms way before they had models for computing. But if you think of as models for computing and kind of fundamentals, it started off around this time of Turing, but also in mathematical logic, where people were formulating these things in the context of propositional logic and many other things. Yeah, exactly. And many of the stuff we borrow from there, like an and, or, not, all of those things are coming from there. Okay, so that's something we'll do. And the remarkable thing is that this model, which is almost like 80 years old, maybe 90 years now, is as powerful as there can be. Okay, there's no other, like, we don't have to second guess ourselves after this model. You'll see it's a very, very elegant model, which will allow us to talk about computing in a completely different language. And it's not just in terms of theory, but the implications have very, very important practical applications, which unfortunately will slightly touch upon this course, but not dig deep into them. Okay. All right. So as a motivating, I think Turing machines, when you see them for the first time, they might seem mysterious, but like, mysterious in the sense that, okay, it seems very ad hoc model, okay? But let's say we start out with DFAs, that's our progression here, right? It's kind of strange that Turing came with, Turing machines even before DFAs, but so we have DFAs already, and let's try and fix it. We saw that they cannot compute some functions. And it told you, okay, this is not able to do what you wanted. You try and fix it. What are some things that you would try first? And then, maybe let's see what is strictly needed, what gives us more power, and at what point should we stop? Okay, let's just think of some things that might help DFS stronger. Okay, so what are the, let's think of again this one-line summary of DFAs, right? Which is, you start from the left and then you make a single pass over the input. And next, constant memory. Okay, so these are the defining characteristics of a DFA. There's a formal definition using transition diagrams and so on. But the main thing, single pass, constant memory. You read a bit, you move to the right, and that's it. You cannot revisit what you saw before. Okay. If I ask you to extend this model, what would be some things that you would think of? Any suggestions? Yeah. Okay, so the first one is multiple passes.
Variable memory.
variable memory. Hold on. I need to give out candy. I'm not taking this home. Daughters will not. Yeah, variable memory. What else? So maybe let me kind of think of more implementable ways of this, right?
Like out of order, like parsing this out of order.
Okay, so out of order. Okay, so this is, there's a name for it. Random access machines, not the album, but the machines. Okay, so multiple passes. One way to think of this is, when you have DFAs, what you really have is that there is, you can imagine there is like a head, there's a pointer which tells you this is the bit I'm reading. I read the bit, I jump to the right. Okay, that's it. I read a bit, I jump to the right. Okay, so one way to implement multiple passes, again, kind of try and connect it to a physical device, is to say, maybe allow our imaginary head, which kind of the pointer to the input where we are at, to move both ways. So left and right. Okay. So the head can now both go left and also to the right. Okay, does it make sense? Kind of fairly intuitive, next step from DFS. Okay, and maybe this is still a bit of a stretch, but you can imagine allowing two-way movement being enough to capture out of order access to. Right? It's just like saying, okay, go to step 100, then to step, go to bit 100 and then to bit 17 to bit 1000. It's like saying, okay, go 100 steps to the right, and then 83 steps to the left, and then so and so steps to the right. Okay. Yeah.
Isn't that basically exactly how an instruction register works?
Yeah. Yeah, exactly. Right. So you can move left and right, and you can kind of, I would say that it might be less powerful than random access machines, but at least it seems like it can mimic its behavior, at least at a crude level. Okay. Does that make sense? And let's think of the next step was variable memory, which again seems very important, right? Often when we think of our algorithms, they do have a lot of memory, right? And this corresponds to having a lot of storage. But remember that we want, okay, so let's say, so give storage capacity that can grow, or let's say that is not bounded. All right, that's kind of giving you a lot of memory. And there's one other thing that we never really address for DFAs versus what we think of memory in our computers, right? So what can we do with memory besides reading? Right. So you can also say, maybe let me give you the ability to read and write to memory. Okay. So I want to give a lot of storage capacity and is writable as well. All right. But we should do this while keeping something fundamental about what we think about algorithms in mind. Okay. So yeah, question? That's a very good question. So there are some problems where we need memory beyond just the input string. Okay, that's like, the suggestion was, okay, why do maybe we allow read and write memory, but kind of only within the input string. And actually, there are questions where you might need a lot more memory than just that. Does that answer your question? Like, that's not enough by itself, but that would have been like, that could have been a nice model if it was sufficient. Okay. On this. All right. All right. I'll give it to you later. I won't try again. Okay, so it gives storage capacity that is not bounded, and it is writable as well. Now, there is one more point that we said at the very beginning, right? So we said an algorithm is a finite answer to an infinite number of questions. Okay. So we can give it unbounded memory, but still we should always have the description of the computer be finite. Okay, because it's not like I'm saying, okay, for each input length, you have a different computer, a longer code for running it, right? We have the same program, like, maybe it's 1,000 lines, maybe it's 2,000 lines, maybe it's 5,000 lines. But the same program should be able to handle, 10 GB of memory, 100 GB of memory, and so on, and work on unbounded inputs. Okay. So this is something to keep in mind, and we will do that. So I would say you already recovered Turing's recipe. You can think of Turing machines essentially as equivalent to having DFS plus left-right movement on input plus read write. Memory. Okay. So the full model that we need is essentially the improvements that you suggested. Take a model of DFA, allow left-right movement on input, allow read-write memory, and we have to tweak it a little bit so that all three ingredients fit together with a finite description. Okay, you don't want to say, okay, your function somehow depends on the memory because memory is growing. How you update the memory should be of fixed length. Okay, does that make sense? You could suggest many other things like, random access machines. That's a very important abstraction. You can suggest maybe you have multiple heads and many other things, but let's just see where we go with this. Okay. And in some sense, the ingenuity of Turing machines is its simplicity. It's just these two ingredients are enough to capture everything else that we can imagine. Okay. So that's what we're going to get to. But let me try and get us started on how to formalize this. So we call it anatomy of a Turing machine. Okay, so just as before, we will have the input. Okay, but we will assume that the input is written in separate memory. Okay, this is again just for convenience. It makes everything kind of clean and simple for us. Okay, so this is input. Let me call it input memory. It's just there. You don't. So let's say the input is also copied onto some memory. Okay, so this is input is loaded into memory. Okay, that's what we start with. And we want the description of the computer to be finite, right? You can't have the description growing. And the way we did it in DFAs was said there are finite number of states which dictate what the machine would do. We'll have the same abstraction. So number of states that is finite. Okay, so let's call this number k. All right. And Turing machine essentially corresponds to the following. You take this picture. Okay, imagine we said there's a pointer here, right? We can say the pointer can go left or to the right when you're in the middle. And we'll also assume that there is infinite memory following the input. Okay, so this is the critical. There is an infinite memory tape or array. Okay, again, it doesn't have to be infinite, but just imagine there's like a very long tape. The input is loaded to the starting of the tape, and you have some head which tells you what bit is being read. Okay, automata would correspond to saying, okay, you don't have those extra cells. You read a bit, you move to the right, you read a bit, you move to the right, update your state and do something and so on and so forth. Okay, so Turing machines will introduce this abstraction that there are potentially cells afterward. You have this head which can move to the right or to the left. Okay, and the head can overwrite. Or let me just say write. Okay, so you can write onto the memory. So maybe
Without restriction.
without restriction. Okay, but only where you are. I can't say, okay, the head is here and you overwrite everything in the entire table, because that doesn't make sense, right? So it's still a very local model. That's kind of very nice about it. You only, what you do, how the machine updates itself only depends on what's happening right where the head is.
So you could rewrite the input if you wanted to.
You can rewrite the input if you wanted to. Again, it's not like, you could say that you can't rewrite the input, but it makes it easier. So let's just allow it. Okay. All right. So these are the three ingredients. You still have a finite number of states, but you have a lot of things afterward. I guess I didn't write it down. Head can move left or right.
One step at a time or any number?
One step at a time. Okay. Again, it's to make it as simple as possible and see where we'll get to. All right. Any questions about this basic abstraction? Seems like we gave our DFAs very limited additional sort of tools to play with. Just some cells afterward and the ability to move left and right and to write onto the tape. Okay. And as we'll see, this is actually this model is just as powerful as any of your Mac M1s. Okay, maybe they'll connect to better to Wi-Fi. Okay, so in next class, when we come, we will make this even more formal. And this is exactly what Turing machines are. Okay. All right, I'll see you all on Wednesday.